Hey friends, welcome back to another special episode of Going Nuclear with Osama. We're joined here with a very special guest. His name is Professor Bereznai, and he is the founding dean of the Nuclear Engineering Program here at Ontario Tech University, Canada's only undergraduate nuclear engineering program. And also, this program has played an incredible role in being a key pipeline into the nuclear energy industry here in Canada. So getting the pleasure to come and speak with him, it's really been a true pleasure, sir. So
Thank you for having me.
It's my pleasure. Tell us a little bit about your contributions to the industry, you founding this program. Tell us how it all started.
Well, I had just finished 30 years working with Ontario Hydro. By then it was called Ontario Power Generation. And I was thinking of doing some consulting work and maybe some lecturing when I saw an advertisement for looking for a dean. It was called then University of Ontario Institute of Technology, looking for a dean to organize a program in nuclear engineering, nuclear energy. So I expressed my interest. I was called by a so-called headhunter for a lunch. He presented the program that was being planned for the whole university. And eventually I was called in for an interview. And fortunately, I just came back from 6 years in Thailand, where I was involved with designing and helping to deliver a complete set of nuclear engineering program from undergraduate, master's to doctorate, preparing Thailand for a nuclear power future, as well as training people from industry. So that whole curriculum I brought to the interview and distributed copies so people could actually see that I know what it would take to plan such a program. And sure enough, after a few weeks of meditation and a further interview with Dr. Gary Polonsky, who was president of Durham College and the university at the time, he was the founding president, I was the first dean appointed for the university. So the first task was to, well, other than meeting a few colleagues who were there to help, is to actually put together a curriculum and present it to the government body that would approve all new university programs. And by the time I was done with that, other deans were hired, and all the other programs were gradually coming online. And by September of 2003, we were ready to welcome our first set of students.
For those that don't know, Ontario, the province that we're here, one of the most populated provinces in Canada, has nearly 60 to 70% of its electricity coming from nuclear power. So tell me about the difficulty in starting such a niche program in nuclear engineering, the only undergraduate program in nuclear engineering in Canada.
Well, historically, typically in Canada, because there were no programs for nuclear engineering, first of all, quite a few of the early engineers were hired from abroad. England had a peaceful use of nuclear power program going back to the late 50s, early 60s. So quite a few engineers and scientists were hired from the UK. And the others, because basically you need a few nuclear reactor specialists, but you also need mechanical engineers and civil engineers, electrical engineers. And the rest of the people with various backgrounds were then trained by Ontario Hydro, especially on the operations side. There was a nuclear training center at Rolphton, close to the very first CANDU reactor that was built. And that school turned out, typically over a 6 months period, a very good quality set of engineers. So that provided some of the material that I worked into the curriculum back in Thailand already. That curriculum was, because this was a CEDA program sponsored by the Canadian government, I made sure that all the Canadian universities that were offering graduate programs in nuclear agreed with the direction I was taking, first in Thailand. And I was hoping that some of the courses would then be adopted when I came back to Canada. So it was one of those fortuitous things that although Thailand still hasn't gone nuclear, all that material that I helped to develop, the individual courses were of course all developed by Canadian experienced engineers and scientists. Typically they would come to Thailand for 1 or 2 weeks. They would prepare and deliver the course material. I insisted that everybody would bring or leave behind a copy of the text, the background material, in effect a textbook for that course. And also, this was the early days of PowerPoint, but already in 1996, 1997, PowerPoint was a recognized medium of delivery, which could then be adapted by the Thais to deliver their own programs. It was quite fascinating for me to watch a typical Thai lecture where they would put up the slide in English, but provide the explanation to their students in their own native language. And then the same material, because Canada was marketing can-dos to China, Indonesia, the Philippines, and to Vietnam, I was asked to go to each of these countries and at least present some of the lectures and pass some of the learning material to the professors in the universities in these other countries. So we're really spreading the can-do message as much as possible, at least in those parts of Asia where there was an interest. And of course, as you know, in China and in Korea, there are operating can-dos.
That's so fascinating that you got a chance to travel and get a chance to spread that knowledge in those countries. I would love to know more about Thailand. How did that all start?
Like so many things in life, I just happened to go to Atomic Energy of Canada offices or an unrelated business, and I had applied for the job, but I was told informally that I was not going to be getting it. They found their own person internally, but for various reasons, that person couldn't take up the position. And because I just happened to go on that particular Friday morning to talk to then Chief Engineer, Dr. Dan Manili, and he said, "Oh, they found you, George." I said, "I didn't think I was lost." No. You're supposed to be in Bangkok tomorrow. So I said, "Sure, why not?" So within 20 minutes, they gave me a pair of tickets. They made sure I had a current passport. I went home, told my wife about it, and she said, "Okay, well, don't get lost on the way. It's far to go." The next thing I knew, I was hired for a 2-year period. But for a number of reasons, it eventually got extended to 6 complete years. And as I mentioned, I was doing some of the teaching, but the bulk of it, of course, we delivered some 50 courses, university-level courses, which were attended by both students of the university at Chulalongkorn University in Bangkok, as well as people from the electricity and related businesses who were interested in developing nuclear expertise so that Thailand could at least develop that option. They already had a nuclear regulator, they already had a nuclear research reactor, but it's a big step from that to a complete nuclear power program. Now, as it happened, Thailand soon after found a lot of natural gas in the Bay of Thailand, but I'm hearing these days they are back to looking at, because as part of climate change, certainly natural gas is not as dirty as coal, but it's still a fossil fuel. If you want to go carbon emission free, nuclear has to provide the base load. Certainly wind and solar are very helpful in covering peak demand, and when the wind blows and the sun shines, they are very effective in producing electricity. But you need that base load at night and when the other methods aren't available, and that is of course the strength of nuclear power. And as I mentioned earlier, in Ontario Hydro started, well, first of all, it's called hydro, which is unique in the world. We don't have electricity to plug into. We don't get the electricity bill in Ontario. We get a hydro bill. People, when I traveled abroad, were quite puzzled about, first, why is it Ontario Hydro, and why is it not called Ontario Nuclear, when at that point, as you mentioned, close to 70% of the actual electricity consumption in Ontario came from the CANDU units. But once Ontario exhausted first Niagara Falls, of course, and then the other hydraulic sites, as the demand kept growing, and in the 50s and 60s it was growing at 7% a year, which was a phenomenal growth. So the only fallback at that time was coal, and Western Canada has brown coal, which is even more unfriendly to the environment than black coal. So Ontario Hydro was mixing black coal coming from the US with brown coal coming from Alberta to add to the generating capacity. And the initial criteria in terms of cost benefit, Pickering had to produce electricity at somewhat lower cost than Nanticoke or Lambton were producing it from coal. And there were very similar plants. Lambton in particular, 4 units, 540 megawatts, just like Pickering. So it was a true comparison of the two methods of generation. And Pickering proved that nuclear could compete financially. It already built up an excellent safety record and an excellent reliability record. And what got me into the business of joining Ontario Hydro, because Pickering was so reliable, the company realized that how are we going to train our operators beyond the first group who made it, who commissioned it. If a unit runs 100% for a whole year, how do you know when it suddenly has to be shut down and then started up, that your operators and your engineers were up to the task? So just like with the aircraft industry, simulators were the answer. And in my doctoral research, I was studying the use of computers, which Pickering was the first power plant in the world to use for controlling the reactor. And that enabled, at least in practice, to have adaptive computer control. So the designers, Atomic Energy of Canada Limited, asked me to look at, as part of my doctoral thesis, the possibility of adaptive, that is online control, changing the control parameters as the operating regime changed. And for me to test my proposed control scheme, I had to simulate the plant. So when I was applying for a job, and even before that, presenting papers on my work, but when I applied to Ontario Hydro, I emphasized that, in my opinion, the simulation I was doing would be a good initial step in building simulators for the purpose of training. And when I got the job offer, they didn't say that it was because of the simulator. I was supposed to be an instructor at the Rolfton School. But by the time I finished my thesis, my first assignment was to look at the feasibility of simulators attached to Atomic Energy of Canada Limited. And one thing led to the next, and I stayed on the simulator projects. I was sent to Montreal to work with the manufacturer, at that time CAE, now H3 Harris, how these simulators are designed. Ontario Hydro, many colleagues of mine provided the nuclear-specific knowledge, and the manufacturer provided the simulation environment, built a hardware replica of the control room. CAE already supplied the digital computer systems for Pickering. So they were the logical company, and really the only company in Canada that were capable of doing it. And by the end of 1976, the Pickering simulator was up and running, and I didn't realize at the time that my future career was defined and set. And what you see behind us here is a simulator for Darlington. So in between, we had simulators for Pickering B, Bruce A, Bruce B, and Darlington, all of them replicas of the actual control room for one unit. What you see behind here, as you know, is a digital graphic display, again, of the replica control room, but it would have been prohibitive hardware cost-wise. And even to recreate all that hardware would not have been practical. So with the advancement of display technology and computers, and of course the good relationship between the university and what is now Ontario Power Generation, or OPG, enabled us to receive copies of the software. We're the only ones who have this software. And each time OPG updated it, we got an updated copy. And in this room where we are, the simulator is now used not only to train people like yourself who graduate from our nuclear engineering program, but OPG sends some of their engineers and technicians and administrators and scientists for extensive training at the university on OPG's Darlington system.
It's so fascinating how you played such an important role in developing these simulators, which are the bread and butter of so much research and so many things to do with operations, right, of the facility. Can you give me a timeline on your when you started in terms of the Ontario Hydro in the simulators? And you said 1978.
Yeah, I graduated in late 1971 and started immediately. So essentially early 72. The government of Canada granted $100,000, which was a lot of money back in 72, to CAE to start developing this feasibility of a CANDO simulator. And I was just one of a number of engineers. Jordan Chow in particular did a lot of the model development and a lot of advice to CAE. He was the design engineer responsible for the simulator. I was the operational person, again with a number of colleagues on the operations side, including input from the station and input from other instructors from the training center. So we put together the training requirements. That is ultimately, you didn't build a simulator to be an engineering tool. We built a simulator to be a training tool. So we had to define what actions, what activities from startup to shutdown, what emergencies had to be simulated. And the way we specified it, it had to be accurate so that experienced operator could not tell the difference between the response of the real station and the simulator. So we would constantly have operators coming off shift, and they experience some event. They would check it on the simulator. They would tell us where we had to tune a bit here, tune a little bit there. So again, many people from the manufacturers, from Ontario Hydro Design, Atomic Energy of Canada. I remember back in those days, I was attached to the station, and all the information was still, you know the expression blueprint? Mm-hmm. Well, all the design was on paper back in that. Designers actually drafted all the wiring, all the equipment, all the description. So I went through, picked out which drawings were relevant to the simulator, which piece of equipment had to be simulated to what level of fidelity, and then physically carried, on the plane, armloads of these drawings from Pickering to Montreal. And I was then attached to the manufacturer for 2 years so that I would actually learn the actual ins and outs of the simulator business. Again, back then, the programs were done on punch cards, and the program was still, the machine was a 16-bit fixed point machine with 64 K of memory, kilobytes of memory. Now you on your mobile device have maybe hundreds of megabytes, probably a few gigabytes of memory. So it's still a wonder how back in those days they were able to squeeze all the equations, program it in fixed point arithmetic into a 16-bit machine and make it look like the real station. And of course today, the software grew and grew. Today on your laptop, you can have all 5 simulations, the Pickering A, Pickering B, Bruce A, Bruce B, Darlington. You can run them on your laptop. That has been the advance just in my working lifetime of the technology. So how, what you will see in your working lifetime is beyond my imagination, compared to what I wrote my first program in Australia on punch cards in 1966, on a computer hand designed and hand wired at the University of Adelaide. And from that to today's, where you just take for granted the internet, that I can now talk to my cousin back in Adelaide, free of charge in effect, see her in living color. It's just been an incredible journey.
It's fascinating how technology has advanced so much in these few years, or in the past couple decades. Tell us a little bit about the importance of simulation simulations, especially after Chernobyl, because I know you probably remember that day that Chernobyl took place. Was there a change in simulation of how operations conducted simulations? Like what changes did that make?
The real milestone came after 3 Mile Island.
Okay.
There were only a couple of simulators in the US at that time, and so much of the 3 Mile Island accident was traced back to, there was both an equipment failure, but there was a definite failure of the operating crew. They didn't recognize what, we all know that water boils at a constant temperature. While it is boiling, the temperature at a given pressure doesn't change. But the actual pressure display instrument was faulty. Keeping a long story short, the operators didn't recognize the condition that the reactor core was under. They shut down emergency cooling, which then resulted in the melting of the fuel. So by the time Chernobyl came along, about 10 years later, there was extensive use of simulation in the world, including what was then the Soviet Union. The problem was that the political masters under communism were more important than the technical expertise. The engineers were running an experiment, strangely enough, to improve the safety of the unit. They were observing, what energy could be extracted from a turbine running down. But there were delays in conducting that experiment because of problems elsewhere on the grid. And by the time it came to run the experiment, the engineers said, no, we can't do it because it'll be unsafe. But the communist leaders at the plant had their orders from Moscow that this experiment had to be run. They overrode the engineers. So the simulator didn't help in that case. The engineers and the operators knew, but they were threatened. If you don't do this, you go to Siberia. So you cross your fingers and you do what you knew was going to happen. So Chernobyl put a lot of pressure on nuclear power, but more the bad media. And as it happened, there was a lull in energy demand. Oil prices came down. Natural gas was found in many places. So the opportunity for nuclear also became much reduced. And it wasn't until well into the 21st century that the demand once again picked up, and especially the recognition that humanity cannot afford to keep burning fossil fuel at the levels we have been, and because the Earth is going to get into a catastrophic weather pattern. So nuclear, as I said, along with conservation and of course solar and wind, but nuclear will, in most countries, remain the backbone of the base load generation.
Yeah, absolutely. And no, it's great. It's interesting to see how the narrative has transformed throughout the years, and now now the world is taking that more pragmatic approach to energy.
Well, both recognition that energy is finite, energy is expensive, so the first step for all of us is to conserve energy, and secondly, to generate it in as environmentally friendly or non-benign way as possible. But the Earth's population has just passed 8 billion, with the downside, if you like, of all this wonderful communication, that people everywhere know how we in North America and in Western Europe live. And it's just human nature to want to improve your standard of living. And that standard of living is directly proportional to the amount of electricity you use. So again, to bring everybody, first of all, we have to reduce our level of consumption so that at least the target to which the rest of the world is aiming to reach is achievable. Now, human population is still increasing, but at a reduced rate. We just have to figure out a way of improving our method of electricity generation and be much more equitable in distributing it to everybody who needs it.
Right now, Canada is building nuclear reactors after 30 years. In my lifetime, this is the first time my generation is going to see these new builds. How is it like when you saw Pickering being built, or back in the day when reactors were coming online in Canada? How's the energy? How's the momentum? How's the energy like? Yeah.
Well, they were very exciting times. To graduate late in '71 and find that the first 2 units of Pickering were already very successful. When I was sent to the Pickering site in '72, Unit 4 was still being commissioned. I was able to go and touch every part of that plant. The reactor wasn't critical yet. I could get on top of the reactor. I was writing models for the moderator system. I could, measure the size of the pipes and how many turns on the valves. Fresh out of school, it's a rare opportunity to be on the leading edge, which I didn't fully realize at the time of what a significant change in technology I was participating in. But then to watch the first 4 units of Pickering A coming online and operating very well, commitments made for Pickering B, and before Pickering B was operational, commitments for Bruce A, etc., to Bruce B and Darlington. They were very exciting times, and we had a very forward-looking government. People were beginning to get a bit apprehensive after 3 Mile Island, and of course much more so after Chernobyl. So for example, the reason Darlington ended up costing so much more than originally planned is that the government put a halt to the construction. Well, there was strong public demand for public hearings. We are hearing about public hearings again today. Public hearings about the safety of nuclear power. And the government committed to stopping the construction until they could verify that, in fact, the term that they came up with was acceptably safe. Nothing is acceptable. Nothing is perfectly safe. You and I could trip on a stairs going down from this building, or heaven forbid, be hit in a car. So there are costs and benefits and risks and rewards to every human endeavor. So, the government and the public hearing defined what was acceptably safe for nuclear power. It was determined that Darlington could be built within that safety envelope. And indeed, Canada has built up an enviable record of nuclear power safety. And again, to be fair to all the other types of systems worldwide. Yes, some 40 people died as a consequence of Chernobyl, but in any other in the coal industry, probably on any given day, that many people die in the coal mines that feed coal-fired plants. Not in a whole lifetime. Well, 50 years of multiply that by 400, so that many reactor years of operation. We had nobody even got hurt or received excess radiation out of 3 Mile Island. Nobody. And about 42 people in Chernobyl. So it is a very safe industry. We know what to do with the waste. Again, it's one of those catch-22s. The public or certain municipalities, certain pressure groups keep opposing the implementation on what is internationally recognized a safe method of disposal deep underground. And my argument is we dig the uranium out from deep underground, from places where nature has concentrated uranium. If we now put that spent uranium fuel or slightly used uranium fuel back into a similar but even more enhanced environment than where it came from, all these stories of, well, it may leak out, it all leaked into a single place. It is not going to leak out from that. There was 2.5 billion years ago in Earth's history a natural uranium reactor. At that time, natural uranium fuel, natural uranium in nature was still more concentrated uranium-235, which is the fissile component, as you know from your studies. And at that time, natural uranium with the right quantity of regular water could go critical. And that has happened there. And all the fission products are still within less than 10 meters. So in 2.5 billion years, rain, earthquake, nothing moved all those fission products. Well, they all decayed by now anyway. And it's a mistake, partly of the industry, to even call it waste. It is very slightly used but radioactive fuel that we take out of the reactor. When we mine uranium, natural uranium is only 0.7% uranium-235. When we take that fuel out of the reactor, the remaining 99% of uranium-238, which can be converted into usable fuel, is still there. So it's like, in some places you can take the oil that was spent in the crankcase of a car and refine it and use it as fuel. So in a way, and in some countries there is reprocessing of the uranium fuel already. But in another 100 years' time, and maybe less, unless, of course, large-scale fusion is realized, that so-called spent and certainly not waste of fuel may well become fuel once again for the more advanced type of reactors. Until then, it has to be safely stored. I personally visited the dry storage at Pickering, wanted to get a sense of just what it is like. I wrapped my arm around one of the big concrete containers. It's just very gentle warmth coming off it. Yes, I picked up a tiny bit of extra radiation, no more than what I would pick up on one flight from Toronto to Bangkok. So I guess, as I said, it's a relative measure of risk versus reward, and I felt it was just something important for me to have a physical sense of the energy coming off from these spent fuels, which first spent 7 years in underwater storage within the plant itself. Then it is moved still within the plant parameters to dry storage. And those facilities are holding it for easily 100 years, by which time, preferably, they'll be moved to underground facility, but if not, they can be housed there for another 100 years. So, in your career, always be aware of the potential danger of nuclear, the potential danger of the radiation, just for yourself as a nuclear worker, for your fellow workers, for the population, living within, like I am, within 10 kilometers of both Pickering and Darlington and feeling perfectly safe. But, be aware of it. It's part of your responsibility that the consumers of that electricity are relying on your knowledge and your honesty and expertise to keep and of your fellow colleagues to keep nuclear power operating safely.
I love how you you simplified the concept of nuclear waste, right? It's such a tricky subject nowadays.
Yeah, it has been. I used to go out as one of the speakers on behalf of back then Ontario Hydro, to meet with church groups and Kiwanis clubs and the like, to try to explain to the average person. And I was well received. There was always a couple of hecklers, much the same as it happened even in Thailand. I remember my secretary came, she did some of the translation, and she kept reassuring them, please listen to Dr. George. He's a good person. He's not telling you stories that are not true. I've worked with him now for, 4 or 5 years. If you can trust me, you can trust him. But it's a measure of trust, and it's a measure of understanding all the, as I said, in everyday life, the risks and rewards of living in a modern society.
So, sir, your career from the 1970s all the way to now, it's been incredible. It's you've contributed to development of simulators, to development of nuclear engineering programs in Thailand, coming here, starting the program. Tell us about the origins. Tell us about your life story. How did you get into the energy industry? Where were you born? Tell us, from the beginning.
Well, I was born in Budapest during the Second World War.
And Budapest?
In Hungary, Budapest, Hungary. The education, most things under communism we criticize, but the education system remained quite strong. So I finished grade 8, elementary, and was attending a technical high school. Second year was just starting when the revolution in October of '56 took place. And that was, very hopeful for the future of the country. So when the Red Army came in and cancelled or quelled the revolution, we were quite depressed. And something like 200,000 Hungarians left the country, most of them going to Austria. I was hoping to go there, but there were delays before my parents finally agreed that indeed the opportunities for me were not as good in Hungary, especially after the revolution. And to tell you the truth, I wasn't all that keen on going to school. So I had an uncle living in Australia. He was a pharmacist, both he and his wife. They went there after the war. Within 6 years, they had a home, a car. They just opened their own pharmacy. So it seemed to me that, there were opportunities way, way better than I have experienced or could see. My mother was working in a pharmacy as a cashier, because by then you needed both parents to work to maintain even a very low standard of living under communism. So it was a combination of wanting to get out of school, get out and work, and start building up and creating a life for myself, with the hope that eventually I could sponsor my parents to join me in Australia. After 8 months of refugee camp in Serbia, because I left it too late to make it to Austria, I took a boat, or I was sponsored by the Australian government as a refugee to sail to Australia. And then reality hit me between the head. Although my uncle and aunt offered for me to go back to school, I had no interest. And of course, when you don't speak the language and you don't have any marketable skills, by then I was 16, the only type of job you can get was unskilled labor. So I got a job bending wires and spot welding at a small workshop that made canary cages and shopping carts. And, I was out in the workforce making little over $10 a day, $10 a week as a 16-year-old. Well, in 57, that was still a credible amount of money. But not want to be able to save up for a car and a home and everything else. So after a while, once I learned enough English, TV was just coming to South Australia at the time. This was in Adelaide. And my uncle suggested that I should go to night school to study radio and TV technician trade. And at that stage, my English still wasn't good enough to be able to understand the lectures, but they gave us very good, it was a private school, they gave us very good notes, so I would go home, translate the text from English to Hungarian, understand what they were trying to say, figure out and remember then the English terms. But I suddenly discovered that by spending that much time studying, I really knew the material. In the first exam, I came third with a 96% in a class of 25. But after that, I was top of the class, and it was a combination of enjoying the process of learning. We had practical workshops in addition to the lectures, so I learned how to use multimeters and soldering irons and how to fix radios and eventually TVs. And very quickly, after a few months of training, I had a job first just to put up the TV antennas, because that's the first step in a city getting television back in those days. But then quickly being able to go out to the homes and fix the TVs. So the company gave me a car to drive, a much improved salary, a much more interesting job. So suddenly it dawned on me that doing a little bit of studying really improves your standard of living and enjoyment of life. And because I was fixing what I perceived to be not very well designed TVs, they kept breaking down the same kind of TV in the same kind of places. I thought I should go back to university and be a better engineer than the ones who were designing the TVs at the time. So I was able to just pick up the textbooks for what was then grade 11 maths and physics and chemistry, and just self-study it, knowing what I knew from my education in Hungary. They were just public exams. You could just turn up for an exam. Didn't have to show that what school you went or anything. I passed those 4 subjects, and then the next year, 4 nights in school, 2 subjects on correspondence. That was my most productive year, while working full-time, 6 days a week, fixing TVs. And did well enough to get a scholarship to go to university to do electrical engineering at the University of Adelaide. So by the time I was 21, I was back full-time in school. And after 5 years of that, again, my results were good enough to get a scholarship to come to McMaster. It's miraculous now that within a month, I had the scholarship. I was a landed immigrant. These days it takes 2 or 3 years to get a landed immigrant status. And came to Hamilton. Within a couple of months, I met a young lady whom I married eventually. So instead of going back to Adelaide after 2 or 3 years of studies, here I am, almost 60 years later. And that education and hearing about nuclear power, and of course McMaster, as you know, had the research reactor right on the campus next to the engineering building. So I took some courses in nuclear power, and then moved into that area of research at the graduate level. Luckily enough, my timing was just right. The simulation I was doing as part of my research was relevant to Ontario Hydro wanting to acquire training simulators. And then that whole work in watching the use of the simulators in training, and I was actually in the early days, I was doing some of the teaching itself relating to the simulator. Just gave me the kind of background which 30 years later somehow made me qualified to start up nuclear engineering at the university level. So you never know. You never know, how one step leads to the other. My only advice to young graduates like yourself and to young students is to do the best you can at what you're doing. I never mapped out this particular career path for myself. Just good thing just came along. I guess people recognized the thing that I was doing well, and luckily I didn't get stuck in things that I was not doing well enough. And one good thing led to the other.
Absolutely, that's an incredible life story, right? How was it like going from Australia to Canada?
That was the easiest of transitions. Other than the accent and other than driving on the right side of the road instead of the left, the two countries are as similar as you can get two countries being physically so far apart. I don't think England is as similar to Australia as Australia is to Canada and vice versa, and the same thing between Canada and the United Kingdom. Canada has been more welcoming to immigrants than Australia was. At the time when I went there in 57, it was still a very strong white Australia policy. That has changed, but Canada was much more welcoming to immigrants in general all over the world. And certainly as an Australian citizen within the Commonwealth, it was a very easy transition for me to go from one country to the other. And it would have been easy to go back, but good job, good home life. Proximity to my parents and the rest of my family certainly were good reasons to stay in Canada. And I've been back to Australia a number of times. I Skype with my cousin at least once a week. It's just so much easier than, back then to make a 3-minute phone call was, a pretty costly affair. You talked in telegram style. Now, in between, I also had the interesting opportunity to go back and work in Hungary. First, Ontario Hydro had an international division where they were marketing many of the skills that Ontario Hydro had developed for its internal purposes. A delegation came from Hungary and looked at the nuclear power plants, and I was called initially just to translate. But once they knew my background in simulators, I was invited to meet their simulator people and meet their engineers at the Paks nuclear power plant. They were interested in enhancing their instrumentation and control technology. And Ontario Hydro actually opened an office. The only international office they opened was in Budapest.
Wow.
And for 2 years, I was living and running that office. Our children were able to get some education in Hungary. My mother was able to live with us for a while. My wife is also from Hungary, so she was able to work at the American school. So, between Australia and Europe and Thailand and Canada, I like to say that I lived and worked on 4 continents, and and try to, bridge the differences between the different countries and bring to each the best that I could from my other home countries and companies.
I know you told me a little bit about your international experiences working with the IAEA. Tell us, share, if you could share a little bit more about that, that'd be great.
Well, the IAEA recognized the benefit of using simulators at a very early stage. And while the replica, the full scope, what we call the full scope replica simulators, are pretty static devices until, of course, this technology came along. What was developed in the mid-1990s, once PCs became popular and capable, what we called in those days micro simulators, that is, or PC-based or basic principles trainers. And the IAEA took a leading role in that, and I was one of the people from Canada who was invited to present what we were doing in terms of can-do simulation relevant to small computers. I was able to then develop course material, and one of my colleagues, also ex-Ontario Hydro, developed a small can-do simulator that would operate on a personal computer. In fact, it's the one that you used with Professor John Froats in your third year of nuclear plant operations. And that was just the beauty of these small simulators, that you could share it within the countries with students such as yourself, and through the IAEA, I was able to demonstrate can-do operations to people, typically 20-25 from different countries would attend these courses. I took the same simulators to Thailand, and some of the courses were run out of Vienna, which was just a 2-hour drive from Budapest, which is always very nice to be able to visit the family at the same time. But a number of them were run out of Trieste in the northeast corner of Italy. It was very special for me personally because in '57, after the refugee camp, I actually got on the refugee ship to sail from Trieste to Australia. So there I was from '57 to '97, 40 years later, not as a refugee back in the same town, but as an international expert teaching others about nuclear power. So, always be an optimist, appreciate the good things, and look forward to even better things to come.
Absolutely, that's incredible, that 360 point of return.
Yes. Closing the loop. So many loops one can close.
Absolutely, that's definitely incredible. And tell us a little bit about your thoughts on the future of new nuclear, like with small modular reactor technologies, with AI and new technologies kind of being introduced. What are your thoughts on the future of new nuclear?
Well, it's certainly encouraging that there is such a thing as new nuclear. The challenge I see is that these are smaller units. So the one at Darlington will be the biggest of the small ones at 300 megawatts. But remember, the original Darlington site was designed for a replica of Darlington A, which is 3,600 megawatts. So we now have to build 12 of these 300 megawatt small reactors to produce the same amount of power. Now the principle is that by building 12 or 1,200 or 120 or whatever number, you can start manufacturing them instead of individually constructing them. So the cost of each, just like the Model T, you can manufacture it on a production line, the cost will come down, and therefore a province or country or a company can afford to buy several of these. I'm just concerned that, and I'm glad that the government in Ontario is now looking at refurbishing Pickering, because if Pickering B were to shut down, another 2,000 megawatts, we just don't have the window to build enough of the smaller reactors. So if we refurbish Pickering, and Bruce A and Bruce B have been refurbished, Darlington have been refurbished, we still will have difficulty producing as much nuclear power until this first one has at least proven itself, both in terms of cost and the timeliness of construction, to start building them. Have to build them more than one a year. to keep up with the kind of demand that I'm pursuing. Because on the one hand, the federal government is trying to bring in 500,000 immigrants every year. Well over half of these come to Ontario, and they all want to live in a similar house to you and I, and consume as much electricity as our families do. But the federal government isn't responsible to keep enough electricity power plants being constructed. So, the province has to have the foresight and the funding, probably in some combination with private enterprise, to keep up with the potential demand. But it is going to be a struggle. I'm certainly glad that we have, as you said, more than 1,000 graduates already from our program. And certainly our enrollment has increased again now that there's the new build is coming along, because my generation is pretty well retired. Even the one after my generation is getting close to retirement. So we need young graduates like yourself to keep the business not just going, but to keep on improving it and ensuring its safety and reliability. So as I said, I'm glad that it's happening, the new build. My only concern is, can we build up the momentum fast enough to keep up with the demand and not have to rely on the natural gas-powered plants over the next at least 10 years before we build enough nuclear capacity. Now, in terms of can-do, the idea of designing a 300 megawatt net electric can-do was recognized back in the late 1990s, but there were certain technical difficulties at the time, and that particular project was shelved. At times I'm hoping that some group of bright young engineers will figure out what was wrong with the problems that couldn't be solved back then with the new tools and new technologies, maybe some AI thrown in, and they can figure out how to build. Again, it's a question of cost effectiveness and safety. Mm-hmm. I mean, Ontario was operating a 220 watt reactor at Douglas Point on the Bruce site back in the late 60s and early 70s. So it's not that can-do cannot be built at that lower level. It's just that the much increased demands for safety analysis were such that the particular design they came up with for a can-do 300 megawatt can-do back in the late 1990s proved to be not cost effective for the level of safety that was demanded by the regulator of the time. And the demands of safety have only increased. It is only now that the designers have to be smart enough to be able to figure out how to use the can-do technology for that level of safety.
1,000 graduates, right, from the nuclear engineering program. Ontario Tech University has this incredible facilities here that we're hearing with all these simulators and many other labs and lecture halls. And tell me about the development of this facility and the energy the energy systems and nuclear science building and all the university. Yeah,
I had always felt, both personally and in terms of my teaching, that nuclear has to be viewed and presented within the overall picture of energy. It's easy enough to make the argument that nuclear power per se, there's nothing much good about nuclear power per se, other than compared to everything else. If you didn't need electricity, or if, as I said, if fusion comes along or some miraculous, easier way to produce electricity, I'm not going to suggest that we should nuclear power around just for its own sake. Although at the same time, as a byproduct, medical isotopes are produced. And in today's hospitals, typically 1/3 of the procedures either use radioactive elements, or the doctor will prescribe some kind of radioactive procedure as part of the treatment, especially in terms of cancer. So, there's a true good benefit side to nuclear power, although people will argue that we can produce those isotopes from research reactors and the like. But I always felt that nuclear power, electricity generation, needs to be looked at within the overall envelope of the benefits of electricity and the various alternatives from an environmental as well as cost-benefit point of view. And in particular, again, most people don't realize that every time we pay our hydro bill or nuclear electricity bill, we are paying for the eventual storage and disposal of all the radioactive components of a decommissioned nuclear plant, including that slightly used fuel. While in terms of the fossil plants, they just put it in the environment until the government started introducing a fee for in effect polluting the environment. For the long history of fossil power generation, they paid zero cost for getting rid of their waste. So that's a huge benefit and needs to be part of the cost-benefit calculation when you're comparing nuclear with any other form of electricity generation. For example, I'm still not sure how well is the recycling of solar panels is known. How well can the propellers and the towers from wind power can be done, let alone all the electrical storage batteries that are really the backbone of alternate generation. So I'm a keen advocate, and a number of our courses in our program cover the lifetime cost and the lifetime energy usage from getting the material out of the mine, refining it, manufacturing the product, using it, and eventually disposing of it. That whole life cycle, the cost of that whole life cycle needs to be looked at for every method of electricity generation. And from what I can tell, nuclear comes out pretty well in most of those comparisons. Certainly if you have a Niagara Fall to make use of, that's pretty tough to beat. But as soon as you have to build up a dam and you have to flood people's land, again, because the demand for food keeps increasing, and food is one of the three essentials. Electricity by itself isn't. It's just an enabler to live better. But the human's ability to produce food in a timely manner to feed over 8 billion people is a trivial matter. And every time we flood productive land to produce more electricity, there's an environmental cost to that. Okay, so in terms of the Energy Research Center, I never felt that I should be asking for a nuclear research center. First of all, the province already has one at Deep River. And we have another one in Manitoba at White Shell. I was involved for a while with the University of Saskatchewan in Saskatoon. There's a wonderful facility in British Columbia. So as a nuclear research entity, Canada is fairly well served. But as an energy research center, where nuclear is part and parcel of wind and solar, hydrogen, our engineering faculty is very heavily involved into the hydrogen cycle. And indeed today we have labs, you mentioned AI, we already have we have some AI facilities, we have some artificial view goggles. So for example, we are working with OPG for a maintainer to be able to go out into the plant and have the procedure for taking apart a valve or maintaining a pump projected onto his glasses. So this augmented reality, which is truly current, is being already implemented, part as a research project, but just like with my work with the simulator, it was always an applied. It was never a theoretical research. It was always development and application and continuous improvement. And always with a clear goal of what is the purpose to which we are putting this device, to train the operators and the engineers to improve the efficiency of the facility and ensure the safety of the plant and of people who are working there. So this building, we're very fortunate when it came to the post-financial crisis in 2006 and 8. the federal government was funding knowledge infrastructure programs, and with the support of the provincial government, the university received $47.5 million, half federal, half provincial. And the fact that it was an energy research center played a significant part in the province deciding to fund this particular building as distinct from a different building on this site or a different building at a different education institution. And the province keeps an eye on the products that we do in terms of the nuclear engineers that we provide. And interestingly enough, while the majority end up working in some aspect of the nuclear power, either operation or design, or part of the nuclear supply chain, some of them work in very different areas. And it's very similar to what I mentioned before, that I came from an electrical engineering background. Many others who work at the plant are mechanical or civil or many chemical engineers and pick up nuclear. I always said to candidates, students, it's a good general engineering knowledge that you're going to gain. And at the time you graduate or later on, you may choose to get into business, you may choose to get into health. And indeed, I'm in touch with a number of our graduates who are working completely outside the nuclear sector and are doing very well.
Phenomenal. It's great that you crafted a center here, a building which develops the fundamental knowledge and skills that these students are now using in the industry. Collectively, like you said, like 1,000 students. Each student probably has a year of around, a lifetime career of around 40 years.
Hopefully,
right?
Yeah. There's a great tendency to retire at 30, start collecting your company pension, and the next day. Yeah. I mean, I'm one of those. I retired after 30 years with OPG and Ontario Hydro, and put in almost 20 years at the university.
Absolutely.
So there's life beyond the very narrow confines of the industry per se. And the other aspect that your question brings back, when we first started the program, the two youngest high school graduates in Ontario at age 15 and 16 applied to our nuclear engineering program.
Wow.
And their mother came to see me as dean and wanted to know, was it reasonable for a 15 or 16-year-old to enroll in nuclear engineering? And would I kind of make sure that they succeeded in the program? And when she heard that I escaped from my country at the age of 15 and started a new life at the age of 16 in Australia, and her husband was working with the international health system in Jakarta, that I had been there and I taught at the university and the research center in Jakarta, she felt so much more comfortable leaving these very young students, in effect, in my care. Now, they did brilliantly. I made sure that no fuss was made. Some people wanted to advertise that we had the youngest high school students. I said, no, give them a chance. Let them be just like everybody else. They certainly looked mature enough. They couldn't drive. The first year, the older wasn't yet 16, so they both had to commute. When they graduated, the younger one couldn't start working because you have to be 18 to be a nuclear worker. Wow. He had to wait 3 or 4 months before he could start work at Bruce Power. So it was just a unique aspect of meeting some brilliant students who did extremely well, of course, and to whom I, in a way, was able to relate at a personal level. And of course, we're still keeping in touch. If I see something on LinkedIn, notes about anniversary or progression, or just bump into them, still living and working in Durham. It's one big family in a way. And of course, the other aspect was being able to hire the faculty. Yeah. You were the beneficiary as well as the other 1,000 grads of the professors that joined this faculty, and it was just great to be able to select and then see them to to share their knowledge and be appreciated by the students. So it's the student body, it's the faculty, and of course the university as a whole. The university was a bit of an experiment at the time. We were the only ones with this mandate to be market-oriented instead of typical academics being inward-looking, academia first, the market, well, good luck to you. And many of them have changed that attitude, to be fair. The other aspect, of course, was that we, in turn, it wasn't enough to be market-oriented in terms of our programs and producing our graduates. We also had to adapt to the market of the academia. All the engineering programs in particular are evaluated by the same Canadian Engineering Accreditation Board like all other universities. So we had to conform to that market. In terms of hiring professors from other universities, we had to conform to that market. So, you think you're going to be a pioneer and produce this brand new university with a totally different mandate and a totally different way of doing things. Well, up to a point you can, but you are also part of that market, and you are influenced by the environment that you are in. And it's been an exciting 20 plus years to see both of those aspects come together and produce the graduates and produce a good name for the university and its programs.
Definitely, I think that mix of industry compatibility, and also that if you want to take the academic route, those two options are great. Do you see other universities, like for example University of New Brunswick or any other institutes, maybe looking at starting up their own nuclear engineering programs?
There has been talk. Certainly University of Ottawa has been looking at it to some extent. And remember that others have graduate programs in nuclear. So, McMaster has a very strong program, École Polytechnique, University of New Brunswick, certainly University of Ottawa. There just isn't the critical mass in demand in any other part of the country. And certainly it would be very difficult to maintain even 2 undergraduate programs in the province of Ontario.
Really?
Because even if we start building a dozen small reactors a year, the current ones are designed. The one we're getting for Darwin is designed in the U.S. So yes, the Canadian or the Ontario supply chain will get involved, and our graduates will get involved. But I just don't foresee enough demand for nuclear engineers to be able to sustain 2 schools in Ontario, unless we turn much more international. And certainly as a can-do focus program like ours isn't really suitable for that. If I were to design a new program and I was assured that it was an international, like the World Nuclear University, if we could establish that as a permanent seat in Ontario and design it with the support of the IAEA as an international center, and we would recognize that, especially in Africa, a dozen countries are each going to build a dozen reactors, and they are all looking for a country such as Canada. It just won't happen. Why not have Egypt? Let's say, there are reactors, power plants are being built in Egypt. There has been research reactors in Morocco. Why not have the African countries have their own African universities run their own African programs? Certainly, part of the success of the Korean nuclear power industry, where they exported the Korean PWR to Abu Dhabi, they also transferred and established a nuclear faculty. So much as I went to Abu Dhabi as well, trying to promote our program, you can't beat when the vendor puts its own money to go and to the recipient country and trains the local Emirati in its own facility and then sets it up as a support there. So ideally, it's a small world, one could see it happening, in practice, I would be much more interested us supporting through the IAEA probably. And a number of my colleagues are working in Vienna at the IAEA, and they may well be involved. And I could see some of my colleagues from here, going like I did. I was teaching at 2 universities in Indonesia, one in Vietnam. I lectured at 2 universities in China. Wonderful opportunities. But to have another undergraduate program just built here would be very difficult to create.
It's good. It's good to know. It's good to get a flavor of what's going on in the world right now, and especially with the 4 units in Baraka and
yes,
and them developing their own industry pipeline. So I think the whole industry, the Canadian industry, really looks up to you, Professor, for this program that you established and for it being a vital pipeline into the world of nuclear. Right?
Well, I've been very fortunate, to have received the knowledge from the industry to begin with, and continuously they keep supporting us. So, we would not have the simulator here if it weren't for OPG's willingness to share it, and the individuals within OPG who will come over and make sure that ours is up to date. So it's all been teamwork. And I've just been blessed with very good colleagues, and I encourage our graduates to keep in touch with each other and to carry the torch forward within the province, within the country, and within the world as opportunities arise.
Absolutely. This was a great discussion. I really, really enjoyed chatting with you, and I'm sure the whole industry really appreciates your words of wisdom and learning about your whole life experiences. Is there any last message that you'd like to give to the audience before?
No, I think you picked me dry. I appreciate the opportunity. It's a unique opportunity for me, and it's great to see someone like one of our graduates to be doing this. And thank you very much for giving me the opportunity.
My pleasure. Thank you, sir.